All right, so thank you everybody for coming. I'm going to talk a little bit about the Antilles Current today, which is a funny little current that many of you probably don't know very much about. So hopefully it'll be interesting. And hopefully with the door closed, I think we don't hear the construction noise. So that should help also. So before I go too far, it's a long list of people that I want to thank here. We've got, some really great folks that have helped out with this, not only all the co-authors, but our technical teams here and in Southampton and across the street at the University of Miami have been essential to this. A lot of the ship operators and so have been really essential to all this. This is a field program that has involved a very large amount of data. So you'll see that there are a lot of people involved in getting us to having a good quality data that we can use for this kind of an analysis. So also, I'd like to acknowledge our funding agencies. Here within NOAA, our funding has primarily been from OMD and from AOML itself, but also our partners have received funding from the National Science Foundation and from NERC in the UK. So a little bit of a history lesson for those of you who aren't familiar. The Gulf Stream studies go back quite some time, a couple hundred years it turns out. And so the top left map here, for example, is from 1685. When people were mapping that out. And that's actually before the Benjamin Franklin map that everybody thinks of as the first one, which is here at the top right. So people have been working on the study of the Gulf Stream in this region for quite some years. It wasn't until kind of the late 19th century that people figured out that, hey, there might be another current in this neighborhood that's headed to the north-northwest east of the Bahamas. And one of the earliest examples that I could find, at least, is here where you can't really see it on the screen, unfortunately, but you have some flow headed that direction east of the Bahamas. They didn't have a name for it at the time. This is from 1853. But they started to recognize that there was some flow in that direction. There's a reason why the Antilles Current was hard to find, and we'll touch on that here in a minute a bit more. But it was around the early part of the 20th century when people started talking about an Antilles Current with that name. But even up until the 1980s, there was still debate within the science community of whether the Antilles Current actually existed as a continuous current and whether it was there all the time or whether it was just a sporadic feature. So to the primary data set that I'm going to talk about today that's going to help us look at this is our Western Boundary Time Series project that's been going on here. One of the really important things to know about Western Boundary, it's built on top of a lot of history of great science as well. So there was the STACS program and the ACCE and the ACCP programs that were run jointly between here and the University of Miami in the 80s and the 90s, and Western Boundary kind of built on top of that starting in 2000. And so we have the well-known Florida Current cable, for example. Data goes back to 1982, and there were ship sections in the 80s, and Moorings started going out in the early to mid 80s. So there's a lot of data sets that came here, and our Western Boundary Time Series project that AOML leads kind of came on the back of that, and basically has done a lot of great stuff in the intervening years. So what you see here in the top map is kind of what's in the water as part of Western Boundary now. We do CTD sections, that's the red dots. We have a bunch of different types of moorings that are out there. Now, this is part of not just Western Boundary, but Western Boundary itself became the cornerstone of an even broader international program. The UK component is called RAPID or some variant of that. It changes every couple of years. The National Science Foundation part is known as MOCA. And so essentially we have these three joint programs that have been working to make measurements east of Florida here since the mid-2000s. So we have a number of different types of moorings. I'll talk to you a little bit more about that. We're going to be focused today east of the Bahamas. Now, east of the Bahamas, we have two different currents. There's the deep Western Boundary Current that's flowing southward below, say, 1,500 meters primarily. We're not going to focus on that today. We're going to focus on the Antilles Current, which is carrying warm water northward. And it's just east of the Bahamas. It's a funny little current because it's not surface intensified, and it's not bottom intensified. The core of the current is in the middle of the water column. So that's one of the reasons why it was hard to find for a lot of folks back in the day. So to give you some idea here, as I say, it's a funny little current. This is an average of 16 lowered ADCP sections that we've taken of the east of the Bahamas over the last decade or so. You can see that the core of the current here in red is at about 400 meters depth. And if you look carefully, it's kind of hard to see on the screen, I apologize, the white contours are the zero contours. So what you're seeing is near the surface, the velocity is almost zero. At 1,000 meters, the velocity is almost zero. So this current is nicely confined in between those two depths with a mid-depth core to the flow at that point. It's fairly narrow. If you look at the resolution of the longitude ticks that I've put here, you can see they're quite fine. We're looking at a fairly narrow current. It's a few tens of nautical miles. So we're not talking a massive current at this stage of the game. You can see underneath it and a bit offshore is the deep western boundary current, these blue contours that you can see underneath here. That's the deep western boundary current flowing to the south underneath it. So now we know that the Antilles Current has impact on potentially both the subtropical gyre and the meridional overturning circulation. As a result, therefore, it has implications for sea level rise, extreme weather events, and a number of other things that we know that the MOC relates to tightly. That's one of the reasons why we want to understand this flow and the purpose kind of behind what we've done here. So we're going to focus on a 10.5-year time period between May of 2005 and November of 2015 for the purposes of my presentation today. And we're going to talk about a bunch of different types of moorings. So I do apologize, there'll be a few technical things that we'll talk about here as I go through to explain the different kinds of data we've collected here. So during this time period, we have had, at almost the entire time, 6 pressure-equipped inverted echo sounders, an ADCP mooring, 2 current meter moorings, 5 mixed current meter dynamic height moorings, 1 dynamic height mooring alone, and 4 bottom pressure recorder moorings. At various times, there's also been a couple of additional instruments above and beyond this, but this is kind of the always there during this time period. And what you can see where these moorings are in the 2 maps that you see there. During the period, we also had 15 research cruises collecting CTD, shipboard ADCP, lowered ADCP, and on one of the cruises, we actually did 2 complete sections through the area. So we actually end up with 16 sections along this, because there was a week apart in between the 2 sections collected on that one cruise. So we have a very large volume of data. For those of you that never seen such a thing before, this is a pressure-equipped inverted echo sounder, for example. That's the anchor off of one of these tall moorings. There's one of the tops of one of the tall moorings. This is being recovered from the ocean. These are all subsurface moorings. They do not have surface buoys or surface expressions at all. So another reason why the Antilles Current is kind of hard to find is if you look at, you can see this, you look at the water properties. So what you see here, the top right, is the average temperature section from those 16 cruises that I mentioned to you. And if you look at that, at first glance, you say, well, there's no tilt to the isotherms. They're flat. And if you look really carefully, right here on the edge, no, they're not. But it's hard to see. It's really hard to find this current. When you look at this initially, you say there's no property signal associated with it. I've kept up here in the top left the average of those sections so you can see where the core of the current is here. If you look at the corresponding place here, and you can see that you can see some hint of tilts in the isotherms. But interestingly, the standard deviation that's shown here has kind of a minimum in the variance right in the core. So that kind of suggests that, hey, this is a really boring current. It's very steady. No, it's not. You'll see as we go forward. Now, if we look at the salinity, you can see there's a bit more tilt in the isohalon lines. So that's giving you a bit more of a hint that we have a current here. But you still see a minimum in the standard deviations. So again, this might give you the idea that it's really boring and not very variable. Even if we look at the oxygens, you still get kind of a minimum in the dissolved oxygen content. as you're going out here. So we typically find in this region these 4 water masses that you see listed here: Atlantic surface water, subtropical, underwater, North Atlantic central water, Antarctic intermediate water. And basically the Antilles is mostly in this North Atlantic central water layer. That's the kind of water that we typically are seeing carried by the current as it flows south. There are lots of different people who've got lots of different definitions for these water masses. Some people like to call this North Atlantic subtropical mode water instead. I'm not going to debate water type names with people because that's a long argument that can never be won. But that's another name that is often used for these waters. So coming back to the types of mooring data, because most of that was all based on the snapshot sections, but most of what we're going to talk about now is based on the time series data, where we've got continuous time series. So we have several different kinds of moorings. We have these dynamic, what we would call dynamic height moorings. These are typically deployed for 12 to 18 months, and they have up to 12 microcat sensors on each mooring. So you're getting measurements of temperature, salinity, pressure at up to 12 different depths, depending on the mooring. They make measurements every, depending on the setting, 15 minutes, 30 minutes, 60 minutes. But in the end, what they do with the process data is give us a 12-hourly measurement every 12 hours. So current meter moorings are typically also deployed for 12 to 18 months, and they have up to 8 single-point current meters on them. A few of them also have upward-looking ADCPs on the moorings at the top to measure near the surface, at 150 decibars usually. And again, these are making measurements every hour, plus or minus, but the final product that they produce out of them is a every 12-hour measurement. So we're doing, these are tall moorings are, of course, the most expensive toy that we're using in this experiment. These are ordered $250,000 moorings each, which is one of the reasons why you don't see a lot more of them being used in the array. The way we're going to use the dynamic height moorings today here is what they produce from the dynamic height moorings is a gridded profile of temperature and salinity from the surface to the bottom. It involves a bit of extrapolation up to the surface from the shallowest sensor, and there are other issues with it, but essentially what they produce is a gridded profile surface to the bottom. We're going to use that to fill the gaps in the travel time records from the pies, because we have a better horizontal resolution of pies than we do any other mooring type here. So that's what we're going to use it for primarily here. The current meter moorings are essentially interpolated both vertically and horizontally onto a regular grid, 20-meter vertical resolution, 500-meter horizontal resolution from these neighboring moorings that are all up on the shelf where geostrophy gets very difficult because it's shallow and the bottom topography is steeply sloped. So in that region, we come up with this gridded velocity product that's based on all of those data. And they are taking into account mooring motion. These moorings blow over in the strong currents. So the sensors are all moving up and down. You have to take that into account as you're doing your gridding. Of course, there's also extrapolation to the surface when you're doing that, so nothing is perfect. But this is essentially the product that is produced from the current meter moorings. We're going to use this primarily right up on the shelf where we can't really do geostrophy very well. And we're going to use it as a reference velocity at one particular depth. And I'll explain more about that shortly. The primary data set we're working with is the pressure-equipped inverted echo sounder. Many of the people here have heard me talk about this before. I do apologize. I know there's people on the phone who haven't heard this before, so it might be a repeat for some of you. I apologize. Essentially, a pressure-equipped inverted echo sounder, or a PIES for short, makes measurements of bottom pressure and round-trip travel time. So it sends out a sound pulse. It goes up to the sea surface, reflects off the sea surface, comes back down, and it has started the stopwatch when it sent it out, stops the stopwatch when it hears it again, so it's giving you a measure of how long it takes for that sound pulse to go to the surface and back. Because the speed of sound in seawater is dependent on temperature and salinity, that gives you information about the integrated temperature and salinity above the instrument during each measurement. There's a technique that is called the gravest empirical mode technique, where we essentially can take hydrography, put together a lookup table of temperature for, in this example that I've shown here, as a function of travel time and pressure. And so we can basically combine this with the time series of data we get from the PIES to give us time series of profiles. You can do this for temperature, and as is in this example, you can do it for salinity, you can do it for density. So basically, the instrument makes a measurement every hour. We process it down to a single value per day. So we have a temperature salinity profile full depth every day above each of the PIES sites from this technique. Let's see. So if we have density profiles, that means we can get dynamic height by integrating that. And so differences of that between two neighboring PIES can give us relative velocity profiles. And the bottom pressure differences can give us the actual velocity at the bottom. So we can combine these two things to get absolute velocity profiles between each pair of instruments. So we can actually get a daily profile of what the average flow between the two instruments is for each pair of PIES. Of course, there are inadequacies in this. Of course, there are some steps that I'm skipping over. But that's the basic concept of how we're using the PIES for this particular technique or for this study. One of the really good things I think about this particular technique is, sure, you can estimate what the temperature is, but you also get from this an estimate of what the accuracy of that is. If we look at the standard deviation between the RMS scatter between the original CTD data measurements of temperature and this smoothed field, you can get a natural error bar. You essentially know how accurate your temperature estimates are. You can do the same thing for salinity and density. So you have a direct estimate of how accurate these things are. So as I mentioned, we're primarily using the tall mooring data, the dynamic height mooring, to fill gaps in the data. And this is an example of us doing that. One of the things that I think this really highlights is the importance of complementary data sets. If you have when you have failures, and you always have failures when you have instruments out in the ocean, if you have complementary data sets, concurrent locations, you can fill gaps, and you can solve the problems. What you see here, the red is, on the left panel, is the actual travel time measurements from the PIES. The blue is when the PIES failed, and we had to go fill it with the tall mooring data. So all of this blue that you can see here is because one of the PIES failed, that time period. So on the right, we've done a very similar thing using the bottom pressure data from those bottom pressure recorder moorings that I mentioned. So we've filled the pressure record gaps from the PIES on the right. You'll notice the gaps aren't the same. That's because sometimes the bottom pressure fails on a PIES, the travel time is still fine, or vice versa. And sometimes we will have, you can see here, we could fill the gap that happened here in the travel time, but we could not fill the gap here in the bottom pressure because it turns out that bottom pressure recorder failed. Didn't come up from the bottom of the ocean, stayed there. It liked it better. So, this is kind of the heart of time series observations when you're doing things in the deep ocean. It's a difficult environment. You lose things. Sometimes things fail. So, but basically, once we've done this, we have an almost continuous record at all of these sites. So that's the exciting part about this particular data set, and that's why this 10.5-year time period was chosen, is we were able to fill pretty much all the gaps in the record. Another advantage of complementary data sets that I wanted to highlight can come when we actually compare the dynamic height mooring data to the PIES data, for example, when they're both working. So this is, on the top panel is temperature, the bottom panel is salinity at 400 decibars, so right at the center of where the Antilles Current is, from one of the particular moorings. It turns out in this case it's what we called Site B. And what you can see here is a couple of things. So the blue is the dynamic height and the red is the PIES data here. You can see they're tracking each other quite well. The correlation coefficient for the temperature is around 0.8. It's around 0.6 for R. This is great. But a couple of things really jump out. You'll notice here in this crosshatched period, the crosshatched period is when the PIES itself failed. And so we've used the integrated temperature and salinity data from the mooring to fill that gap, to give us a travel time, and then to use that with the GEM method to estimate profiles for the comparison. What you can see here is really surprising. We see huge spikes in the blue. This is the actual mooring data, not the PIES, not anything. This is the actual mooring data. We're seeing huge spikes. With this, we were able to identify that we knew the top portion of this mooring had broken off and floated away. We thought that the data had been corrected well enough that this was not an issue. The moment we did this comparison, we saw that sure enough, no, the extrapolations to the surface had not actually been done well. And we were getting huge spikes in the mooring data during that time period. This was going into the MOC calculations that everyone uses. So this can be important. Another thing that really jumps out here, if you take a look at the salinity, notice the last year and a half. They're going really well. And then suddenly, the blue goes down. With this, we were able to identify a failure in the calibration of one of the microcaps that was on the moorings. And so we were able to help fix that. So this is, I'm not in any way trying to say pies is better than moorings here. It's not. Everybody says the gold standard is the tall moorings, and I would agree. They're expensive, but they're the gold standard. But there can be times when having the pies nearby can really help you identify problems. Shenfu.
So is that the marking used for the MOC calculation?
This one is one of the moorings that's, yes, used.
The time is right at the time where the MOC had destroyed frequency, right?
Yeah, the 2009 time period, yes, is when that's going on. This is not one of the crucial moorings. This is not the one that's closest to the western boundary. This is the one that's immediately east of it. So it is part of the calculation, but it's not one of the most important ones. So I haven't actually looked to see if we would see similar sorts of things at the most important one on the west side, because we didn't actually have a pies at that site for about half of this time period. That particular site, which is what we call A2, we only had enough money to put a pies at that site about halfway through this time period. So we don't have a good data set to compare with that one, as well as we do at B. Rick.
I have a dumb question. So during that crash period, you're calculating the speed of the travel time from the dynamic height mooring data.
Correct.
And then running it through.
Correct.
So I don't understand why they differ.
So the key is the integration. So essentially, we're integrating temperature salinity from the surface to 1,000 meters, essentially, when we're doing the mooring data to fill the gap. Whereas this is very specifically right at 400 meters, which is above where the break happened in the mooring. And so it turns out the integral of the data below that was sufficient for us to get a more reasonable number out of the gem fields than what the mooring is getting with its extrapolation. It's a pure extrapolation up.
Okay.
Does that make sense?
Yeah, I think so.
Yeah. So.
As is probably the gem technique.
The gem technique essentially is, in some sense, a filter. It's an empirical filter. The key thing to remember with the gem technique is that there's no normal modes. There's no parallel isotherms assumed. It's a pure.
Actual CTD profiles and not poorly extrapolated.
Correct. Correct. So essentially, we look at it's kind of thinking of it as you're getting an integrated heat content in a sense between the surface and 1,000, and you're going into the lookup tables from the CTD data to say that heat content should give me a profile that looks kind of like this, and not like spike, So essentially, that's what's going on with there. Yeah. So now we've got all of these different data sets. Let's talk about what the Antilles Current looks like. Hopefully, I didn't put you all to sleep already. So what you're seeing here is 5 different sections of the Antilles Current from each of the 5 different data sets. So, and I do apologize, the labels dropped off. There are labels in my computer upstairs. So you're going to have to trust me on which ones these are. On the right, we have the 2 geostrophic methods, the pies and the CTD. On the left, we have the direct velocity measurements, which is the current meters, the shipboard ADCP, and the lowered ADCP. We can figure it out from the legend, or from the caption, if you're curious which is which. A, B, C, D, E. So the top left is the current meters, the top right is the pies, middle left is the SADCP, middle right or lower right is the geostrophic relative to the surface, and the bottom left is the lowered ADCP. There were labels on my computer. I'm sorry, but I don't know what happened there. So this is what you see. Now, one of the things to pay attention to is on the bottom of each panel is the resolution of the data. Notice it's very different. So there's a lot more resolution on the shipboard ADCP data, for example, than there is in the current meters or in the pies. The other thing to remember is with the geostrophic, you'll always have a single velocity profile between each pair of locations. So there is between this instrument and this instrument is a single velocity profile that represents a true integral between the two sites, but there's only a few profiles here. There's more here in the CTDs. So, but one of the things that really jumps out to me as you're looking at this is, hey, we've got 5 different systems. They're all clearly measuring an Antilles current. It's looking pretty good. But the next thing that says is, hey, take a look at the left side versus the right side. The geostrophic methods, which are the right side, all seem to be a bit stronger than what you're seeing in the direct velocity measurements. That's a bit of a surprise. And we're going to talk a little bit more about that as we go forward. So if we integrate the transport between sites A and A2, which are the first 2 pies, the first 2 cyan diamonds that you see there, it's kind of the core of the Antilles current. Is right there, in there. If we integrate that, then we get these transport per unit depth profiles. These are the average. What you can see here pretty quickly is the red, which is the pies, red solid, and the blue, which is the current meter moorings, are quite different. I mean, clearly they're measuring a current in the same location, but there's a significant difference in the amplitude. Now, if we want to compare the ship sections to that, it's a little bit unfair at first because the ship sections represent a small subset of days during this 10.5 year time period. So what if we take the mooring data and average them only on the days when we were doing the ship sections, the 16 days of the ship sections? Then we get the red dashed and the blue dashed. And then if we lay on top of those the other measurement systems, the LADCP and the SADCP are the green and the black. The CTD relative to the surface is the magenta dashed dot. Hey, once again, the geostrophic methods are agreeing extremely well. The direct velocity measurements are agreeing extremely well. And the two don't agree particularly well with each other in terms of amplitude. It's clearly measuring the same current, but there's an amplitude bias between these two. And the sign of that is a bit of a surprise because we often think of ageostrophic flows as increasing the strength of a flow. Think of cyclostrophic, for example, in the Gulf Stream. There are many studies showing the cyclostrophic term can increase above the geostrophic, but here the geostrophic is actually bigger. So that was a bit of a surprise for us. And not to step on myself, but we don't have the ultimate answer. So that's still something we're going to have to understand. But I think it's really an exciting result to try and understand why that's happening. If we go to the next pair of instruments offshore between A2 and B, which is a bigger span, almost 3 times as wide, and we do the same kind of a comparison, we see a couple of things. First, the 2 full 10.5 year averages are much closer together, except for this problem here near the surface in the shear in the pies, and I think that's actually a pies problem, a pies gem problem. I think the moorings are probably right there. And then if we average again only on the set of days when the ship sections are happening, everything is kind of collapsed in on each other together. So all of them are pretty close. And again, the pies and the current meters are agreeing extremely well up until you get to about 250 meters below the surface. So this disparity between the geostrophic flow and the direct velocity measurements seems to disappear as soon as we get out to the flank of the Antilles current. It's really only showing up right in the core. So I think that's an area for future study. We're going to need to try and understand why are we seeing this. Now, setting that aside, because unfortunately I don't have the answer to it, we'll just keep going and talking about what the Antilles current looks like and what the variability looks like now instead of the mean, which we've been focusing on. So if we take a look here, this is correlation of temperature and salinity from the site A, which is the westernmost of the pies, to all of the other sites in the array. And what you can see from this, on the left, we see the correlation coefficient. On the right, you see the lag-lead relationship where the maximum correlation is found. And what you're seeing from this is westward propagation. What we're seeing here is motion of about 9 centimeters a second is what seems to be the temperatures that you see at the offshore sites show up at the site A at a speed that's associated with 9 centimeters a second. Now, this is not a completely new thing. Sylvia and I have done work here before where we saw things that were propagating across the array. We had focused on the deep western boundary current before, but the same things are going on in the upper water column. It's a little faster than what we saw before, but we got a much longer time series now than what we had done previously. So perhaps we just have better statistics because we have a longer time series. People have been finding these primarily barotropic, westward propagating features here for a long time. That's totally not new. What is new, perhaps, is that this is really dominating the temperature salinity variations that are existing in the Antilles Current. It doesn't appear to be something that's propagating with the flow. It doesn't seem to be pulsing in the Antilles Current. It seems to be driven primarily by what's coming from the basin interior, is what we're seeing with the variability. So if we integrate the transport of the Antilles Current in here, I'm going to define it as between the surface and 1,000 decibars and between the coast and site B, and that's based on that mean section that I showed you earlier, because that seems to be where the average boundaries of the Antilles Current are. You get the red and the blue lines here. Red being the pi's version, and the blue being the direct velocity from the current meters. What you can see is obviously we're measuring the same thing again. The correlation coefficient between these time series is almost 0.9. So clearly measuring the same thing. The RMS difference is around 4 sphere drips. There's a 1.9 sphere drip difference in the means. Again, this seems to be perhaps a bias issue, an amplitude bias. Particularly that jumps out if you look at the difference between the two, which is the black line here in the lower panel. If we then correlate that difference with the original time series, what we find is there's pretty high correlation with the pi's data. So that's suggesting that, again, this is suggesting an amplitude bias. The geostrophic velocities are higher consistently. So when the difference is high, it's because the geostrophic velocities are high. It seems to be a correlation there. There seems to be an amplitude bias in what's going on in the variability, just like what we saw in the time mean profiles. Another thing to point out, and I didn't mention it, is this is really highly variable. We have a peak-to-peak range of 50 sphere drips here. This is a big, highly varying current. So although the mean is fairly small from the pi's data, it's only 4.7 sphere drips, the variability in this region is quite large. Remember that 50 sphere drips, because I'm going to come back to that in a little while. So we look at the spectra of the two time series we were just looking at, the blue and the red. They're essentially identical to within the error bars. So again, the current direct velocity measurements and the geostrophic measurements measuring the same variability. The variations are the same. The timescales of variability are very, very similar. There's nothing really jumping out. It's just there seems to be this amplitude bias between the two time series. The only previous studies looking at spectra of the Antilles Current time series were from papers led by Tom Lee, who used to be a faculty member across the street here at Rasmus back in the 90s. And he was finding peaks near 30 days and 100 to 150 days. Well, if you look at these spectra, there's no peaks at those timescales. Probably this is because we have a much longer time series, again, than was available to Tom in those days. They were using mainly 1 to 2 year long mooring records. We've got 10.5 years. So we're much better resolving most timescales because of that. We have a lot more realizations, essentially. Another thing to keep in mind here is the error bars on these spectra, which is something that people don't talk about very often. The error bars on their spectra are huge at some timescales. So you see, for example, here, these two vertical black dotted lines are the annual and semi-annual periods. There's this huge peak you see here at these semi-annual periods. So, aha, there's a semi-annual cycle to the Antilles Current. Carefully look at the error bars. The error bars at that frequency include 0. There's a huge variance in how much energy is there in different portions of this record, obviously. And so you could, if you didn't pay attention to the error bars on this, you might start interpreting this semi-annual cycle as being physically real and meaningful. but our own statistics suggest that we're not even really sure it's there, that there's even a peak at all at that time scale. So it's something to keep in mind when you're looking at spectra is, do they have error estimates on those spectra, and are they being realistic about them? And here's the kind of the nugget of that is, here's the seasonal cycle of the Antilles Current. Again, the red is from the pies and the blue is from the direct current meters. We see once again there's a bit of an amplitude bias. The phasing is essentially identical between the two, but there's a bit of an amplitude bias. The error bars that one would put on these are up there in the top left. When you look at that, you might say, oh, there's a semi-annual signal here. Here you got one peak, here's another peak. So we have a semi-annual signal maybe. But those two peaks are not outside these error bars. These error bars are one standard error bars, so 67% error bars. Clearly, none of this is statistically significant. Maybe this peak to that peak is statistically significant at the 67% level, but it's really not statistically significant, despite the fact that we have 10.5 years. So you'd think that if there was a strong seasonality to the flow here, it would jump out because we have a long enough time series. But the heart of the answer to that is take a look at the peak to peak. We're only talking about a little bit more than 5 sphere drips. I mentioned earlier the peak to peak on the time series is 50 sphere drips. So what we're seeing here is there's a huge amount of aliasing of other time scales into the seasonal variability when you do something like this. You have to pay attention to the fact if you're trying to pull out a seasonal cycle, is there actually enough of a seasonal cycle to get a statistically meaningful thing from the length of record you have? I think what we're finding here is no. Even though we got 10.5 years, do we really know what the seasonal cycle of the Antilles Current looks like? No, if there is one. And we can't even really prove there is one with this time series. So it demonstrates kind of the importance of long time series. It demonstrates paying attention to your statistics as you're going through these things to figure out what we want to say. And the same thing is true in many ways about the Gulf Stream just to the west of here, just in the Straits of Florida. The seasonal variations there represent less than 10% of the total variance. Basically, we get similar statistics here. So it takes a long time before you can actually get a robust seasonal cycle. In the Florida Current, we figured out it took you 25 years before you could get a robust seasonal cycle out of the Florida Current. Here, it's 10.5 years is not enough. I think we can say that now. So wrapping up in some conclusions here. The Antilles Current, and I do apologize, I had all kinds of jokes for this that I was planning to do because I was originally going to do this seminar on Monday. And it was going to be April Fool's Day, and I was going to make this a little bit more fun and enjoyable. And then we had visitors on Monday, so I had to move the seminar, so I took all the jokes out. So hopefully it's, still, kept you at least a little bit awake. So the Antilles Current is carrying 4.7 sphere drips or so northward during this time period. The huge peak-to-peak range, the standard deviations are around 7.5 sphere drips. So it's varying quite rapidly on the daily timescales. The pies-based and the geostrophic and the current direct velocity measurements are getting very similar Antilles currents, but there does seem to be this amplitude bias between the two. So the two data sets are excellent and really useful for filling gaps. It really demonstrates to me the importance of having overlapping data sets and to have multiple measurement systems when you're trying to do a long-term study like this, because instruments will fail. But they can also help us identify failures within the data sets like the examples I showed you earlier. But I think really the most interesting and exciting result out of this is this geostrophy versus direct velocity measurements. What does this mean? I don't think we have an answer for that yet. We have looked at things like, is it the direct wind forcing right there? The Ekman flow, the Ekman transports are much too weak in this narrow current, because remember, we're only talking about a current that's a few tens of nautical miles wide. In that area, it's not just the direct winds. That's much too weak. What is causing the disparity? I don't have an answer for you. It's something that will hopefully bright young people in the room. We'll figure out, longer time series may help us figure out, looking in the models may help us figure it out, although the Antilles Current is not really well represented in a lot of models. So the models may need to improve their resolution horizontally and vertically before they're going to be usable for this. But that's kind of where one of the areas I think it should be a future study area is trying to actually understand the dynamics of the Antilles Current and how is it that the geostrophic flow seems to be stronger than the direct velocity measurements. So, and I should have said it when I went through the slide, but I didn't say it. Some people might argue that the reason why the geostrophic is stronger is that maybe the direct velocity measurements are too widely spaced, and so you're missing the flow in between. It's really not the case here. The moorings are really close together, and the shipboard ADCP is essentially horizontally continuous, and it shows the same answer. So it isn't just that simple answer that it's the direct current meter velocities are too far apart and are missing something. I don't think that's the answer. So the answer is something more complex. So for more details, we've got a paper that's under review at the moment at JGR, and I'd be happy to take any questions.